Good evening, everyone. So my talk is about the limitations of deep learning and about how the field of AI is going to evolve to overcome these limitations. Deep learning, current limitations, and future perspectives. So um, basically, I would like to look at deep learning as a technology and zoom out by a large factor. So can we try to look at deep learning as it is today and look at its previous history and at its current limits and try to see the road ahead for AI and deep learning? And so first, a few words about where I come from, which is what informs my perspective on this topic, on AI and deep learning. So I do deep learning research at Google, and I created the Keras framework, which is an open source toolkit that makes it easy to develop deep learning models and makes deep learning accessible to more people beyond just experts and researchers. And today, about 1/3 of people using deep learning in the world are doing so using Keras. So that's about 150,000 users, almost 160 now. And Keras is now included in TensorFlow, Google's big deep learning genre, symbolic computation framework, which is open source, because open source is very important at Google. That's why we made TensorFlow open source. And now TensorFlow is the most widely used machine learning repository in the world. And so on the side, I also do AI research at Google Brain. So some of it is in computer vision, and some of it is on how to apply deep learning to formal systems. So for instance, how can we use deep learning to prove mathematical theorems, which is not something that deep learning is supposed to be good at. So in order to understand the limits of deep learning, first we need to understand what deep learning really does. So I'm sure most of you already have a pretty good idea what deep learning is and how it works, but let's get it out of the way quickly. Like, what's deep learning? Deep learning is not this. I know there's a lot of hype around deep learning, which typically serves to hide its true nature. The hype around deep learning gives it this aura of mysticism, in particular when people compare it to what the brain does. But in fact, the human mind has very little to do with what deep learning is. So deep learning is more like this. It's a parametric model that fits some data. And the most surprising thing about deep learning is actually how simple it is. Before 2010, so before the big rise of deep learning that we just saw, no one really expected that we would achieve the sort of results that we got today on perception problems. So things like image classification and speech recognition, just by using these big parametric models trained on lots of data with high descent. And the big surprise of deep learning is that it turns out all you need is sufficiently large and sufficiently deep parametric models trained on sufficiently many examples. So the big surprise is how this really simple idea turns out to work extremely well on machine perception and pattern recognition, even large amounts of human training data. So let's take a quick look at how exactly deep learning achieves this. So in deep learning, everything is a vector. So basically everything is a point in a geometric space. So you start with some input data, which could be images, text, videos, sounds, and so on. And you vectorize it to form an input space, which is a geometric space, right? And then you map this space point by point to a target space with a deep network. And the target space could be, for instance, image labels if you're trying to do image classification, or it could be transcribed words if you're doing speech recognition. And this mapping from space to space, so this geometric transformation from one space to another, is done via a stack of so-called layers. And each layer itself implements a very simple geometric transformation of one space into another. And so you have a chain of geometric transformations, which together implements a complicated transformation from mapping so this input space to a target space. And one thing we should note about this geometric operation is that it has differentiable, which is required in order for us to be able to learn its parameters via gradient descent. So differentiable, intuitively, it means that this geometric morphing must be smooth and continuous, which is a huge constraint, as we will see soon. So if all this story about geometric morphings and differentiability is confusing, you can intuitively visualize it in 3D if you try to imagine someone trying to flatten a crumpled paper ball. So the crumpled paper ball is the input space that you start with. It's the initial manifold of your data. And each finger movement that you apply on the paper ball to uncrumple it is similar to the geometric operation done by one layer. And the full sequence of gestures that goes from the crumpled paper ball to the flat piece of paper is equivalent to the transformation operated by the entire deep network. You could say that deep learning models are mathematical machines for uncrumpling these complicated manifolds of high-dimensional data. So here, the paper ball is a 3D example, but typically you're dealing with data that has millions of dimensions, not just 3. So that's really the magic of deep learning, is to turn meaning, so things like text and image, into vectors, so into geometric spaces, and then to learn geometric morphings from one space to another, one layer at a time. And it turns out all you need are spaces of sufficiently high dimensionality, and that's sufficient to capture the full scope of relationships found in the original data. But one very real risk with deep learning is that of misinterpreting what deep learning models do and to overestimate their abilities. Because as humans, we have a tendency to project intentions and beliefs on the things around us. That's our theory of mind. And applied to deep learning, this means that when we are able to somewhat successfully train a model to handle a human task, like generating captions to describe pictures, for instance, like in this example, then we are led to believe that the model understands what it's doing. But actually, deep learning models do not have any understanding of the task, at least not in a human sense, because they are trained on a very different task than what we think they're doing. They're trained to map an input space to an output space. That's all they know. And that's just a proxy for the actual task, like captioning. Image captioning actually requires, understanding what's going on in an image. But when a deep learning model does it, it's literally just operating a continuous geometric transformation from a space of images to a space of sentences. And that's just a proxy for the task of captioning. Because our own understanding of images and sounds and language and so on, it's grounded in our experience as humans. And machine learning models, they have no access to such experience. So they cannot understand their inputs and their tasks in any way that humans could relate to. So the only success of deep learning so far has really been mapping an input space X to a target space Y, given large amounts of data. And just to be clear, that is a game changer in just about every industry. This is a very simple idea that's applicable to a tremendous scope of very important problems in machine perception, pattern recognition. So let it be said that I am not in any way downplaying the significance of deep learning. Deep learning is immensely useful, but we should keep in mind that deep learning does not solve AI, right? Because this geometric morphing that deep learning implements does not, in fact, model human thinking. Because of that, deep learning is terrible at a lot of the things that humans are really good at. For instance, deep learning is not capable of reasoning and planning and abstraction, which are fundamental components of the human mind. And at the end of the day, deep learning is only just good at this one thing, which is pattern recognition, which is machine perception, in the form of mapping one space to another, given lots of data. So to highlight this difference between humans and deep learning models, let's take a quick look at a couple examples. And they're kind of silly examples. They're not like real world problems. So one example, let's say that you want to find the proper launch parameters that will get a rocket to land safely on the moon. So if you were to use deep learning for this problem, then you would be learning a dense mapping between the space of initial launch parameters and the outcome associated with these parameters. And that would require launching millions of rockets until you could properly explore the search space, until you could properly find good outcomes, find good launch parameters. And on the other hand, if you're human, then you don't need millions of launches, you can actually use your reasoning abilities to figure out an abstract model of the problem, which is rocket science, right? And you can use this abstract model to derive correct launch parameters using very few trials, using very few launches, essentially just the number of launches that you need to validate your model. In a similar way, if you're trying to use deep learning to teach some kind of robot, some kind of human body to navigate urban environment and avoid cars, then you would need to be learning a dense mapping between your sensory motor space and your outcome, like whether or not you're dying. And that would require actually dying millions of times, because you can only learn things that you directly experience, right? And of course, if you were to be dropped into a new city, then your input space is significantly different, so you have to relearn a lot of things. And remarkably, humans, they're capable of learning the same thing. They're capable of learning to avoid cars without having to die even once, right? Well, hopefully, because they can learn things that they do not directly experience. That's the power of abstraction, right? They can learn from other things than experience. Learn, for instance, from imitation, learn from language. They can imagine what's going to happen next. They can ask, what if something happens, and so on. So this brings us to a fundamental difference between human capabilities and deep learning, which is that deep learning is only capable of what I call local generalization. So it can only operate close to data that it has already directly experienced, because that's what pattern recognition does. And on the other hand, humans are capable of covering vastly more ground using comparatively very little experience. And that's what I would call extreme generalization, which is a sort of generalization that's enabled by reasoning and abstraction, which deep learning is incapable of doing currently. And just scaling up current techniques by adding more layers to our models and training on even more data is not actually going to get us any closer to solving AI. So we need fresh ideas to overcome these current limitations. And I believe a necessary evolution that we can expect in the field of machine learning is a move away from these models that perform purely pattern recognition and can only generalize locally, towards models that are capable of abstraction and reasoning, so that can achieve extreme generalization just like humans. And current AI systems, some of them can achieve some basic form of reasoning, but they're all hard-coded by human programmers. So for instance, any piece of software that relies on search algorithms or graph manipulation and formal logic and so on, it can perform planning and reasoning and so on, but it has to be hard-coded. So these systems, these algorithms, they used to be known as symbolic AI, right? Back in the days when people didn't associate AI primarily with machine learning. Now, when you say AI, people believe it's machine learning, it's deep learning. But there used to be this huge field of symbolic AI, and I don't think it's dead, right? I believe that we'll start developing AI systems that will blend together geometric intelligence, so things like deep learning, and symbolic intelligence, which you can think of algorithm, basically. So geometric intelligence provides capabilities for intuition and pattern recognition, while symbolic AI provides abstraction and planning and reasoning and so on and such. So they're very complementary. And one early example of what such a hybrid system could look like is AlphaGo from DeepMind, the Go AI, which blends deep learning for doing some things like evaluating a board position in a game of Go or predicting your next move. And it blends it with an algorithmic module that runs Monte Carlo tree search. But one thing to keep in mind is that AlphaGo was hand-designed and hand-programmed by human engineers. But in the future, such a system could be learned end-to-end from data, starting from high-level algorithmic primitives. So essentially, you could have an AI, and you give it a new task, like Go playing, and it would be able to quickly assemble primitives. So some of them would be symbolic, like doing Monte Carlo research, and some of them would be geometric, like using a coordinate or something. And so the AI would come up on its own with the solution program, with the AlphaGo program, basically. So that's basically I think, the way of the future. So in the future, AI models will not just be these differentiable geometric transforms mapping an input space to an output space that are current deep learning models. So instead, they will be closer to general purpose computer programs. So programs that are learned, which is the subfield of AI called program synthesis. So these programs will involve advanced algorithms and data structures, and not just very simple operations like matrix multiplication and convolution like what we do today. They will involve graphs and tree search and sorting operators and many more. And they will be learned automatically. So they will not require human engineers to develop them. So of course, such AI programs, they cannot be learned via gradient descent because they wouldn't be differentiable, like programs that typically aren't differentiable. And differentiability is way too strong a constraint. Most programs that one might want to learn from data, they cannot be realistically expressed as a differentiable geometric operation. And even if they can, such an operation might not be learnable from available data. So we need to go beyond gradient descent and beyond backpropagation, which are our tools today, towards better search algorithms, more general search algorithms that can do discrete search in particular. And there are many candidates in this space. Some early candidates could include, for instance, evolution strategies, or analytical algorithms, or ADMM, and so on. It's a very kind of new and fast-moving field. So you should keep your eyes on program synthesis. I think it's a field. It's been around for a while, but it's seeing definitely a renewal, and it's just getting started. So if you follow this vision and AI models get more complex and similar to programs, and they're built on top of richer algorithmic primitives, then this increasing complexity is going to require more sharing and more reuse across different problems, rather than training a new model from scratch every time we have a new task or a new data set, which is what we currently do. And that's tremendously inefficient, right? Because a lot of data sets do not contain enough information to develop a sufficiently complex model from scratch. So it will become necessary to leverage information that comes from previously encountered problems. To think about it intuitively is, for instance, you don't learn English from scratch every time you open up a new book or you read a new article. That wouldn't even be possible. You have to reuse your existing knowledge of language, because in a single book, there's not enough information to learn an entire language. So machine learning models in the future will involve sharing programs and sharing representations across many different tasks, and maximizing model use, so essentially maximizing learning efficiency. So in summary, the long-term vision for the future of AI and deep learning is a process for learning models from data that closely resembles the workflow of software engineers today when they're developing software. So if you want to know how AI will look like in the future, then you can look at how human engineers operate today, and it's probably going to be similar. So if you think of the process of software development today, once an engineer solves a specific problem, like a well-contained problem, like parsing JSON files, for instance, then they will package the solution as an abstract and reusable library, and they'll put it online. They will open source it, like we did with TensorFlow and Keras and so on. And so that in the future, other engineers facing a similar problem can simply search for existing libraries. They can download one and use it in their own project. They don't have to reinvent the wheel with every new project. So engineers are constantly manipulating abstract programs that were developed on a different task than what the engineers are currently doing. And that's a kind of abstraction that is the holy grail of AI. So I believe AI will be evolving along these lines, along the lines of creating new programs using existing abstract primitives, and these primitives will be shared across many different problems. So in summary, in the future, given a new task, you will have a meta-learning system that will be able to quickly assemble a program to solve the task using very little data, which will achieve the sort of extreme generalization that we are talking about. And this is done by assembling existing modules from a global library of shared modules. And some of these modules will be algorithms, some of these modules will be geometric transforms, like deep learning models, like convnets and so on. And the geometric modules provide intuition, and they provide pattern recognition and perception, while the algorithmic modules provide reasoning and planning. And when such a meta-learning system would find itself developing similar program subroutines for several different tasks, then it could come up with an abstract and reusable version of the subroutine, and would store it in a global library. That's how you build up the global library over time. And such a process would be implementing the capability for abstraction in string generalization. I mean that a subroutine that's found to be useful across different tasks can be said to be abstracting away some aspect of problem solving. And that's a definition of abstraction that's very similar to the notion of abstraction that you have in software engineering. So you could say that such a meta-learning system is successful would be implementing what we call an artificial general intelligence, an AGI, extreme generalization, basically just like humans. So that concludes my talk. The content of this talk was adapted from one chapter from my book, chapter 9. So my book is called Deep Learning with Python. It will come out at the end of the month, or maybe next month. It's currently undergoing. So if you want to learn more about these ideas, you can buy my book. For engineers who want to get into deep learning, so it's very practical programming experience, but not too much. So this concludes my talk. Thank you very much for listening. And once again, I'm very sorry that I couldn't attend Francis AI in person, but hopefully, thank you.
Okay, thank you, François.